All right. So as we look at this expression here, a few different ways we could go about this. One thing to do is one of our ways of simplifying is through converting everything to sines and cosines. That can, in a lot of instances, be beneficial for simplifying and canceling, which is the method that I took here. So I converted secant to 1 over cosine using reciprocal identity, and tangent to sine over cosine using a quotient identity. And then from there, I was able to cancel out cosine and secant, because we can cross cancel cosine and cosine, so we just get 1 in the numerator. So we have 1 over sine over cosine. So to simplify that fraction, we multiply by the reciprocal of the denominator. So doing that to the top and bottom in both cases allows us to cancel out that denominator of sine over cosine. So then I'm just left with 1 times cosine over sine, which cosine over sine gets me to cotangent. Potentially other ways you could go about this as well. Perhaps converting tangent to 1 over cotangent, and then multiplying by cotangent over 1 on top and bottom, so that you get cotangent up top first, and then converting to sine and cosine, so getting rid of that fraction first, and then converting could be a way to go about it too. Either way, you can get to that correct solution of cotangent. All right. Today we are going to be working with proofs of trig identities. Now I know in the past, particularly in geometry, usually students are not a big fan of proofs. However, in this case, I have found that a lot of students actually prefer proofs as opposed to what we've been doing so far, because it's a lot clearer where we need to go. You have a clear idea of a starting point and an ending point. So some of you actually may find these a little easier and a little more doable than simplifying. And I actually quite like these, but I'm a math teacher, so that makes sense. They're kind of fun. They're like a puzzle with 2 pieces where you create the rest of the pieces. So we'll be doing some proofs. So there are 2 parts to proofs. Number 1, showing your steps, so getting from A to B, and number 2, explaining those steps. So we're going to have to do both of those things, keeping in mind all of those identities that we've learned and had throughout the course of this unit. So things like reciprocal, quotient, Pythagorean identities, those things will all come into play. So having your notes out from that first day of notes last Thursday with those identities would definitely be something that's beneficial. So we're going to jump right into that very shortly. And you'll have a chance to, hopefully, depending on how much we get through, get started on that IF by the end of the hour. All right. So there's a lot of writing here. I'll let you know what I think is most important. So when we're proving trig identities, or verifying. So verifying and proving, they mean the same thing. Our goal is to transform one side of the equation into the other. So it's not to touch both sides of the equation, change a lot of things on either side, and get to your solution. The key thing we need to do when we're given a proof, when we're told to show or to prove that one thing equals another, is you just pick one side and try and get that side to look like the other. So our guidelines, these are definitely the most important things for today. So understanding our guidelines and what we need to do to write proofs. So what I have bolded is definitely the most important pieces. So number one, only use one side. So if I'm asked to prove, you don't need to write this down, but if I'm asked to prove that sine equals 1 over cosecant, your goal, you cannot do things differently. You can't change sine and change 1 over cosecant to get them both to equal something different that's the same. You have to pick one side of the equation, doesn't matter which side, and you have to stick to it. So when we're working through proofs, you cannot work from both sides of the equation. You pick one side and you make it look like the other. In most cases, we pick the more complicated side. So that's why I have that written there. But there are ways to work from either side. It doesn't necessarily matter. Some sides may be easier or less steps to work from. But we'll talk through some of that as we do some proofs. Our second guideline is to use known identities. So that's what I'm talking about, as in like reciprocal, quotient, Pythagorean, etc. Because we need to make sure we can explain things. So you can't go and make up things or use things from outside sources. You use the identities that we've discussed and that we know, because those are the things that we know to be true. Now, sometimes when you're proving things, an identity might not be helpful. Like maybe part of the proof is just addition or canceling common factors. So you can do that. You just say addition or say cancel common factors. So you don't necessarily always have to use identities between steps. Sometimes just algebra is your proof or your reasoning, but we will definitely be using a lot of those identities. And as we use them, they'll start to come into your brain a little bit faster as we get more practice. And this last one isn't so much a guideline as it is more of a tip. So I guess we really only have two guidelines necessarily. Converting to sines and cosines is almost always beneficial. Sometimes you have to convert to sine and cosine and then convert back into something. But when we convert to sines and cosines, that's usually when any sort of canceling takes place, which can definitely be beneficial. So usually in most cases, if you're getting stuck, if you're not sure what to do, where to go, try converting to sines and cosines. You will see that when we're doing proofs, there is a little bit of a guess and check type of process here, like there is with simplifying, where you can try something and get stuck and have to restart. But that's okay. It happens. It's part of the process. And sometimes you just have to restart. But proofs are beneficial because you do always know where to stop, because they tell you what the end point is, what the result should be. Whereas with simplifying, sometimes you can't tell when to stop. You don't know, can I simplify this more? Is there a way I can combine things? With proofs, it's very, very clear, which some of you may appreciate. All right. So this is our first proof. So it says verify the identity. Verify means the exact same thing as prove. So if you see the term verify, it means prove. So again, there are two things we need to do. Number one, we need to actually get side A to equal side B, or vice versa. Number two, we need to explain our reasoning. So the first thing we do here, and our goal is to verify or to show that sine over tangent equals cosine. So the way that we show that is by getting either sine over tangent to equal cosine, so showing that it can equal cosine, or doing the opposite, showing that cosine equals sine over tangent. Cosine is easily the most simplified side. It's usually easier to go from complex to simple than simple to complex. So what I'm going to do is I'm going to focus on transforming or finding a way to show that sine of x over tangent getting that to look like cosine. So there are a number of things we can do. One of our methods for simplifying is just to convert to sine and cosine. So that's what I'm going to do first. What I want to do is I want to rewrite tangent as sine over cosine. So that is my first step. So that's what I've changed. So notice how I'm writing this. So we're starting with sine of x over tangent equals cosine. So I'm showing the process of that second step. So what I'm doing now is I'm going from sine over tangent to sine over cosine. So what I did, or my reasoning, is I used the quotient identity. So that quotient identity, remember, where we have an identity that says tangent of x equals sine over cosine. So that's the identity that I'm using. So notice I don't have to list explicitly that tangent of x equals sine over cosine. That's not part of my process. But I do need to say what identity I'm using. We have a name for it. So that's what we represent. So with any of these identities, a lot of them fall under categories. Like there's 6 reciprocal identities. You don't need to say like reciprocal identity of sine or something like that. You just say reciprocal identity. Okay. And what you're seeing here, so this is what I expect to see in terms of you showing me your proof. So this whole thing that's written is your step. With proofs, you need to make sure to really show your work and really explain your reasoning, because what you're doing is you're proving something. You need to show me why something's true. So at this point, we have things in sine and cosine on the left side. Again, we don't ever want to do anything to the right now. Once you've started changing things on the left, you have to leave the right as is. So what I can see here is we probably want to simplify this fraction. So that's what I'm going to do next. I'm going to divide these fractions, or multiply both top and bottom by cosine over sine. So doing the same up top. And we need to show that that's what we're doing. So notice I'm not just like writing this as cosine. I'm showing that I'm multiplying by the reciprocal of the denominator, or cosine over sine. What I'm doing is I'm dividing these fractions. So when we're listing this explanation, it doesn't require an identity or anything. So you need to say what's happening. So I'm not going to be super specific on or particular on what you show me here. You just need to tell me what you're doing. So I'm dividing fractions, or you could say multiply by the reciprocal. Anything just to give me a quick little explanation on what you're doing. So I'm multiplying by cosine over sine. And in my next step, what I'm doing is I'm canceling out those signs. So we can just say simplify fraction, or cancel factors. So canceling factors of sine. Anything just to describe what's happening. And at this point now, the left side equals the right side. So that's when I know I'm done with my proof. So I've taken the left side, I've shown how to get it to the right side or how to make it equal, and I've explained each step along the way. So what I've written over here on the right, these are just different things you could have. You don't have to say divide fractions and multiply by reciprocal, or simplify fraction and cancel factors. I'm just looking for an explanation. The last thing is I have this little box colored in. So that's the symbol we use to say our proof is done. Or also the letters QED. QED is some acronym for a Latin phrase that basically means I'm done with the proof. I don't remember exactly what that phrase is, but we just either draw that little box and color it in or write QED. That just means I'm done with my proof. There's nothing more for me to do. This is complete. It's kind of like a period on a sentence. So we do it's form. It's something that we want to make sure we write. Good, Ben. I'm glad it's not as bad as you thought. Questions on that first one? Awesome. Thank you, Ben, for that, for the expanded acronym. Cool. All right, I can't say this enough. You can only do things to one side of the equation. I say it over and over and over every year with this, and there's still students that do things to both sides. If you do things to both sides, you will get it wrong. It's not correct. You can't do that. You can only change one side of the equation. So you have to pick a side and go with it. Now there are ways you could change. You could start with the right side. It'd basically just be kind of working backwards. Usually it's a lot harder to start with the more simplified side, but that is valid. You are welcome to do that. Okay. All right. So here's example 2. So we'll go through this one together. Then I'll give you a chance to try one on your own here. Oops. So for this one here, we are verifying. So again, that means proof a new identity. So as we look here, we need to start just by picking which side do I want to work from. So if I pick the left side, that means I need to find a way to make this left side equal sine squared. If I pick the right side, I need to find a way to make this left side equal cosine theta times secant theta minus cosine theta. So you are welcome to choose either. As I look here, it probably makes a little bit more sense to choose the left side because it's easier to simplify things than to expand. So that's what we will do. So as we look here, it might not be super clear what to do, but essentially we just kind of want to try things, see what we can make work. One thing I'm noticing here is that we have sine squared as our goal. So having things like secant might not be valuable. So converting things to sines and cosines could be helpful. I see Ben suggesting distribute cosine. Yeah, sure. Let's try that. So let's try distributing cosine. Or what did I do? We'll go about it this way. So let's distribute cosine first. So we have cosine of theta. Should have the theta key times secant theta minus cosine times cosine, which is cosine squared of theta. So that's my first step here. So I need to describe what happened. So usually I just do like a little arrow to show what's described. If you want to, I don't know, put your description in brackets or something, that's fine. Anything to just distinguish, this is my description. And what I did was I just distributed. So I'll just say distribution. So it doesn't have to be anything fancy. Like you can say distributed property, that is what it is. But if you want to just say distribution, that's fine. So we have cosine secant minus cosine squared equals sine squared. So first of all, something I'm noticing is that our end product has to be something squared. We now have something squared. So that makes me feel like we're on the right track. We still don't have everything as sine and cosine. So let's convert this secant here to 1 over cosine. So that's an identity that we're using. So we need to make sure we describe that identity. So the identity we're using here is the reciprocal identity. So I want to make sure to write that. Oh, identity. Just my color. So I performed that reciprocal identity here, converting secant to cosine. So as we look over here and as I look at descriptions, I should be able to make those connections. I should be able to see, well, so what's changed? If I'm just someone random reading this, I should see, well, the difference is we go from secant to 1 over cosine and use the reciprocal identity. Okay, that makes sense. So at this point now, what we can do is we could cancel out our cosines here to get just 1, because that's cosine over 1. So I have 1 minus cosine squared equals sine squared. And for my description here, I could say simplify fraction. You could say something along the lines of cancel cosine or cancel common factors. Anything just to tell me exactly what happened. So I'm saying simplify fraction, which sounds kind of vague, but it's the only fraction here. And it does look pretty clear that that's what happened when I look over my work. At this point, now we need to continue to simplify. So what I'm noticing is we have sine squared, we have cosine squared. Anything squared to me screams Pythagorean identity. So remember, we have, you don't have to include this for your proof, but we have that Pythagorean identity that says sine squared plus cosine squared equals 1. So let me tell you first what you cannot do. So you may be looking at this and you're like, oh, let's just add cosine squared to both sides and then we've got that identity. No, you can't do that. So you cannot change both sides of the equation. So if I add cosine squared to the left, I have to add it to the right, and that changes what's on the right side. Cannot do that. You can only change one side. Once you select one side, you change that and you leave the right side the same for the entire problem. So this has to say just sine squared the entire problem. So, but what we can do instead is we can rework this identity potentially so that it matches what we have here. So within this identity, we can subtract our cosine portion. So that it matches what we have here. So when we subtract, we get sine squared equals 1 minus cosine squared. So it's still the same Pythagorean identity. It's just reworked. So cosine 1 minus cosine squared is equal to sine squared. So what I can do here then is I can substitute sine squared of theta in for 1 minus cosine squared. So I have sine squared equals sine squared. And what I just did was I used a Pythagorean identity. So that's my explanation. Pythagorean identity, because that's what I did, that's what I used. At this point, my left side equals the right side, so what I've done is I've proved that cosine times secant minus cosine equals sine squared. So I am done. So I show that I'm done by using my math period, my proof period of this box that is colored in. Okay. So there isn't necessarily always one method or one way to go about proving identities or verifying identities, just like there isn't always one method to simplifying. You could start by using that reciprocal identity first and then distributing. So you could easily flip those first two steps. Or there are other ways you could go about this, potentially maybe working with sine squared. So we could rewrite sine squared as 1 minus cosine squared, and then try to find a way to get that to equal the left side. There are different ways to go about it. But as long as you're only working from one side, showing your steps, and using your identities and algebraic properties correctly, you should be okay getting to the finish line. Questions on that second one? Okay, so keep in mind the identities that you know. We'll continue to use those to help us prove things, and hopefully as we get more and more practice, that you'll be able to recognize where those identities fit a little bit better. Okay. All right, here's one for you to try. So again, we're verifying, so that means prove. Sine plus cosine times cotangent equals cosecant of x. Keep in mind our order of operations. Multiplication comes before addition. So you could look at this or treat this problem like it looks like this. That may be beneficial to some of you. So I'll give you about 4 minutes here. Do your best with this one. At least give something a try. Remember, converting to everything to sines and cosines sometimes can be helpful because it can help you simplify things and cancel things. That doesn't mean it's always going to work, but it's always a good thing to try. So I would recommend simplifying the left side into the right, but that's up to you. It is your choice. So I'll give you 4 minutes. Give this one your best shot, and then we will talk through one possible solution together. All right. Let's start to talk through one method. If you took a little bit of a different route, that doesn't mean you're incorrect. It just means double check, make sure you've got those correct identities and explanations. If you're looking over and you want me to check it, you're welcome to send me a picture or something. I'm happy to look over and make sure your proof looks good. So the way that I chose to go about this was converting to sines and cosines. So I started by taking cotangent and rewriting that as cosine over sine. So that's using a quotient identity. From there, what I did was I took cosine and cosine over sine and multiplied them together. So I just performed some multiplication. That's why multiply is my second step. From there, lots more happened. What I chose to do was to rewrite this as one fraction. So what I noticed was that on the right side, we just have one trig function or one term. So I made sure to get a common denominator here. Let's see, let me use something so I can identify. To get a common fraction. So I found my common denominator of sine, meaning I multiplied sine by sine over sine to get that same denominator. Can you repeat the last step? Yeah. So let me just reiterate where we're at. So I started by converting cotangent to sine over or cosine over sine. So that's using the quotient identity. Next, what I did was I multiplied cosine and cosine over sine. So cosine times cosine is cosine squared. 1 times sine is sine. So I multiplied that fraction. My next step was getting these two terms into one fraction. So what I did was I multiplied sine by sine over sine so that we have a common denominator. So sine times sine is sine squared over sine. Sine times 1 is just sine. So I found a common denominator is what I did next. I multiplied sine by sine over sine. From there, I added my fractions together. So since I have a common denominator of sine, I can add sine squared and cosine squared. So I'm just combining those fractions together up top. At this point now, what I see is I see that we have sine squared plus cosine squared. Well, we know from our Pythagorean identities that sine squared plus cosine squared is 1. So what I did was I substituted sine squared plus cosine squared for 1. And to do that, I used the Pythagorean identity. Lastly, 1 over sine is cosecant. So I rewrite 1 over sine as cosecant using a reciprocal identity. It's cosecant equals 1 over sine. So with those identities, anything that's equal to each other means you can substitute for each other. That's what being equal means. It means they're the same, just a different visual representation. And then now that I've got the left side equaling the right side, we're all set. So as I look at this problem initially, a little hard to tell exactly what to do. So sometimes you just have to try things. And we tried converting, we tried putting things all in the same fraction, and it did work out. That's not always going to be the case. Sometimes you might get to a point where you're not really sure where to go from there. So that doesn't necessarily mean that you need to start over. It might mean you need to just like look at your identities a little bit, see if there's some things you can substitute, but it could mean starting over might be the best bet. So whether that means looking at the other side instead or trying a different method from the same side you just started with. So starting over is not a sign of defeat. It's okay if you need to retry, rethink some things, try a different process. There's nothing wrong with that. Questions on this problem? Alrighty. How many do we have left here? Just 2. Cool. Alrighty. So this one is looking a little bit more complex. So again, same process, verifying identities. As we look here, both sides are a little bit complicated in my opinion. But one side is probably a little more complex than the other, that being this side here. In my opinion, working from the right side is probably going to be easier because we have 2 fractions here, whereas on the left side there are no fractions. So it's usually easier to combine fractions and cancel than it is to expand. So in my opinion, starting from the right side and working with the right side is probably going to be the better process, but you can choose to go from the left as well. So as we look on the right side, differences here. So we want to make sure to get the right and left equal. So the first thing I notice is we have 2 fractions, so 2 terms on the right. On the left, we have no fractions and just things multiplied together. So combining things is going to be a good step for us. So we need to think about how can we combine these 2 fractions on the right? Well, the way that we combine is by getting common denominators. So what I want to do here is I want to combine these fractions, so that means get the same denominator. So I'm going to multiply the first fraction by 1 plus sine of x over 1 plus sine of x. I'm going to multiply the second by 1 minus sine of x over 1 minus sine of x, so that I can have the same denominator. So what I'm doing here is I'm getting a common denominator. So I'm taking, I'm taking this first fraction here and multiplying it by the denominator of the other. So my first fraction I'm going to multiply by 1 over sine plus 1 over sine. My second fraction I'm going to multiply by the denominator of the first, or 1 over sine over 1 over sine, so that I can get a common denominator. So that's the first step that I'm taking here, is getting a common denominator. Notice I've selected the right side to work from, so now the left side should always stay 2 tan of x secant of x. Left side is always going to stay the same though. So what I'm doing is I'm choosing to get it into 1 fraction. So we're going to take the next steps to get to that point. And if you're seeing connections and want to work ahead of me, by all means, go for it. Just make sure you're checking periodically to make sure you're getting to that correct solution. So now what we can do is we can subtract these 2 fractions. So I've got my common denominator being 1 minus sine times 1 plus sine. So I'm going to subtract 1 minus sine from 1 plus sine, because we just have 1 times and 1 times. So we're just going to subtract these 2 fractions. If you wanted to do this into 2 steps, so first take a step to multiply these fractions within themselves and then subtract, that's fine too. But what we're doing is we're subtracting the fractions here. Next, what we can do is we can distribute this negative and we can simplify the numerator. So we're simplifying the numerator by subtracting. So 1 minus 1 gives us just 0. Sine minus negative sine, or sine plus sine, gives us 2 sine. So if you need to see more of that, we're taking 1 plus sine of x and distributing that negative. So negative times 1 is negative 1. Negative times negative sine is positive sine. And then simplifying. So 1 minus 1 cancels to 0. Sine plus sine gives me 2 sine. Down below, we're also simplifying. So I'm going to multiply. So 1 times 1 is 1. 1 times sine is sine. Negative sine times 1 is negative sine. And negative sine times sine is negative sine squared. So sine and negative sign cancel, so we left with 1 minus sine squared. So that's how we get to there. So what we did was we just simplified the numerator and denominator. So you don't need to say more than that. You could say like subtract in the numerator, multiply in the denominator, or FOIL in the denominator. You can be more specific as you want, but all we're doing is we're just simplifying this fraction. So this puts us in at least a little bit of a better spot. We've got it down to just one term. At least I'm hoping it's better. So another thing that I'm seeing here is sometimes it can be helpful just to look at differences. We've got sine squared. We don't have anything squared here, so that may come into play. I'm also noticing we do have a sine squared, particularly 1 minus sine squared. So anything squared tells me maybe the Pythagorean identity could be a decent step. So we have used that Pythagorean identity of sine squared plus cosine squared equals 1. Definitely a helpful identity in the past. And it looks like we could reuse this identity. So if I subtract sine squared from both sides, so we can rewrite this identity as cosine equals 1 minus sine squared. So we can use this Pythagorean identity. So let's try that. So if we substitute in cosine squared for 1 minus sine squared, we've got 2 sine over cosine squared. Now, as I look at this final problem, we have the 2, so that feels good to me. We need to find a way to get tangent and secant from sine over cosine squared. So we need to think about how can I make this work. Well, I know tangent is sine over cosine. So we've got 1 sine and 2 cosines here. Secant is 1 over cosine. We've got another cosine down here. So I think there's a way we can make this work with quotient and or reciprocal identities. So let's start by just separating cosine squared into cosine times cosine. So anything squared, remember, is just something times itself. So I can rewrite cosine squared as cosine times cosine. And I just separated it into 2 fractions here just to clearly distinguish. I mean, you could easily write this as 2 sine x over cosine x times cosine x. It would be a sufficient equal step. But now in this case, I'm starting All right, sorry about that. My internet just went out. Let's get back to where we were. Okay. So we separated into two fractions, and I'm sure a lot of you are seeing the next steps we can take. So we know sine over cosine is tangent, and 1 over cosine is secant by the quotient and reciprocal identities, respectively. So that's what we do next. We convert sine over cosine into tangent and 1 over cosine into secant. So you can separate that into two steps. You could do sine over cosine to tangent in one step, and then 1 over cosine to secant in another, or you can put them in the same as long as you're describing or writing both identities, showing the description, an explanation for each. Okay. Questions on that one? Okay. Oops. All right. Let's do. Wait on this. Oh no, there we go. Okay. So you have one problem left here. What I'd like you to do is attempt this problem on your own. So pick a side, determine which one you want to convert into the other. And once you're finished with that, you can check your solution by clicking into this presentation in the week at a glance. So we've only got 4 minutes left, and I want you to get a chance to get a start on it. So attempt this problem, check to see if you have a similar solution in the week at a glance. As long as you're able to get to the correct place using the correct identities, you should be in a good spot. So do your best, try something. If you're getting stuck, you can check into this presentation for a little bit of help. But I do want you to give it an attempt on your own. There's an IF that's posted on Google Classroom. It is due on Wednesday. So you have tomorrow as well to continue working through that IF. There'll also be a few more practice materials for you to work through tomorrow on your asynchronous day. But don't feel like you have to complete this IF today. You will have a little bit of time to work on it tomorrow as well. So we got about 3 minutes left. So take this time to make a little bit of progress on, I can go back to that problem, on this last problem here. When you're finished, check your solution in the week at a glance, and then you can get started on your IF. Are the cosecant x's able to cancel? They are not. So you can only cancel terms if everything's multiplied or if they're factors. So since we have this subtraction here, you can't just cancel the cosecant. So if it were cosecant of x times sine of x, then that would be a situation where you can cancel the cosecants because everything's just multiplied together. So we would consider these both to be factors. But whenever you introduce addition between factors, that's when you can't cancel. So in addition, like if this were even like this, if this were sine of x plus 1, but it's still contained within a factor, then we can cancel that cosecant. But because we have that subtraction outside of factors, you cannot cancel cosecants. Good question, Caleb.